Okay, I had mentioned online that after reading your homework and reading some of the emails and comments you guys made, several of you had questions about harmonic motion, polar coordinates, polar equations and conversions, and problems involving bearing. So I just wanted to make this video. I might end up making like 2 or 3 of them based on how long the video is because I'm limited with time. But I just wanted to run through a few examples to give you guys a better idea of how to solve the problems. So first off, we're going to start with polar coordinates and polar equations and things like that. And the major thing to keep in mind is we're not changing anything. We're not moving a point around. We're not moving it from one quadrant to another. We're just finding a different way to label it. Essentially, you can say something is a foot long or you can say it's 12 inches long. They're not different. It's just different ways of saying the same thing. It's 1 foot long or it's 12 inches long. It's still this long. Same principle here. If I have some point in the plane, say this one right here, I can label that point different ways. If I want to label it in rectangular coordinates, the ones we are used to in terms of horizontal and vertical, then I find the x value, for the sake of argument, we'll say it's 4. And I find the y value, for the sake of argument, we'll say it's 3. And I get the point 4, 3. That's what we're used to. Now I want to find the equation or the point in polar coordinates. And essentially the idea is, well, with polar coordinates, I need to find, instead of the horizontal and the vertical, I need to find this distance right here. We call it a radius, r, but I need to find this distance. And then I need to find an angle. This angle right here, theta. Keep in mind when you do these angles are from the horizontal right here. So if I ended up with an angle over here, I would have to use the angle starting at 0, going all the way to that quadrant, or all the way to this quadrant. So just keep that in mind when solving these out. But now essentially, I just need to find r and theta for that particular point, and then I can label it in polar coordinates. And we had said before in some of these other videos we've done that essentially, well, this r, well, I can just draw a vertical line right here. And now I get a right triangle. We know this side is length 4. We know this side is length 3. And now the Pythagorean theorem says r is just 4 squared plus 3 squared, that's 16 plus 9, 25. Square rooted, and r is 5. So I get my radius just using the Pythagorean theorem. Then I have to find theta. And there are different ways to do it and different points you can use. Generally speaking, on the off chance you do the math wrong, try to use the information you're given. In this case, we're given 3 and 4. So do I know a trig function that relates theta, 3, and 4? Well, yeah, this is opposite, that's adjacent. TOA, that's tangent. So I can say tan theta is equal to opposite over adjacent. And now how do I get theta? I take tan inverse. Theta equals tan inverse of 3 over 4. And let me just grab a calculator. Let's see. And we get tan inverse of 3 divided by 4. And I'm going to change to degrees for this. And you get 36.8 degrees. So we'll say this is 36.8 degrees, which tells me this angle is 36.8 degrees, which tells me this is 36.8 degrees. And now we have our polar point. And again, the point is, this point did not move. It did not change. We just labeled it in a different way. In rectangular coordinates, find x, find y. Find the horizontal, find the vertical. In polar coordinates, find the radius, the distance to the center, the distance to the origin, and find the angle from the horizontal. And you're done. One other thing to keep in mind, for the sake of argument, suppose we did the exact same thing, but I moved it over to the second quadrant. So say, let's see, we'll say this is 4 or -4 based on how you want to look at it. This is 3. and then I want to find the polar point right here. In rectangular coordinates, well, that's easy enough to do. It's -4/3. In polar, well, I need a radius and I need a theta. The radius, it's still the Pythagorean theorem. This is still going to be 5. That's not going to change. For my theta, I would do the exact same thing. Tan inverse of 3/4 or 3/-4, however you want to look at it. And you'll get theta equals 36.8 again. But the answer is not 36.8 degrees. Remember, these inverses are restricted to certain quadrants. That's my reference angle, which means this angle is 36.8 degrees, just like it was up there. But the angle in polar coordinates starts here. So the angle I want is actually this one. And now you can do the math to figure it out. That whole thing is 180. So this angle is actually 180 minus 36.8. 10 minus 8 is 2, 9 minus 6 is 3, 7 minus 3 is 4, and I think it's at 143.2, if my quick math is accurate. And just keep that in mind. I want to say when grading your homework, some people gave me the wrong angle because you were saying giving me this angle, not this angle. Just make sure you know where your angles are being measured from and find them correctly. The math to find the particular angle you want is pretty straightforward, as long as you know the angle you're looking for. The trick you can use, which we have mentioned in one of the other videos, if you use this angle 36.8, you can actually, if you plug this in and you plug the -4 in, you'll get this angle right here, -36.8, which sends you down here to this quadrant. And then there's a trick which some of you used in your homework. If the negative angle sends me down here, but I know my point's supposed to be over here, I can use a negative radius, because a negative radius reflects to the other quadrant. So you can just as easily write this as -5, -36.8 degrees. Ultimately, there's an infinite number of ways to actually write that out, so it is somewhat open-ended. Generally speaking, we try to write them with as many positives as possible and get rid of the negatives. So you would prefer this one, but this works just as well. It's the exact same thing. One of the things that came out of this, and I'm not going to rehash all the math to solve it because we've already done it, but if you draw a triangle, you can get these equations that relate polar coordinates and rectangular coordinates. And the equations are x equals r cosine theta, y equals r sine theta, the Pythagorean theorem, x squared plus y squared equals r squared, and then we had tan theta equals opposite y over adjacent x. And these are really important. And we'll use them both in this section and on this exam, as well as in a lot of the stuff we do throughout the rest of the semester. So we want to make sure we understand these. So, for the sake of argument, suppose we have this equation right here in rectangular coordinates. 3x plus 2y equals 6. I want to write that rectangular equation as a polar equation. All that means is I have to get rid of the x and the y and write them in terms of r and theta. There are different algebraic ways to do it. Ultimately, the most simple direct substitution is best. And in this case, just substitute. We have 3x. X by definition is r cosine theta. So just substitute plus 2y. Y is r sine theta equals 6. And now I actually have a polar equation. It's all in terms of r and theta. Some of these you can simply algebraically manipulate to make them look nicer. Other ones, it doesn't work that way. For the purposes of this one, if you want to solve for r, you can factor in r out of both terms, and you get r times 3 cosine theta plus 2 sine theta equals 6. And now divide this whole term over, and you get r equals 6 over 3 cosine theta plus 2 sine theta. And you're done. You have a nice simple equation in terms of r and theta. both of these are fine. This is implicit, this is explicit. And again, some of them, like this, will be easily transformable into an explicit form. Other ones they're not, and you can just leave it in the implicit form. The goal is to understand how to algebraically use these formulas to translate a polar equation, to translate a rectangular equation into a polar equation. So one more. Suppose we have r equals 4 cosine theta. That's a polar equation. I want to write it as a rectangular equation. And essentially the principle is the same. Before we had x's and y's, we had to replace with r's and thetas. Now we have r's and thetas, we have to replace with x's and y's. There are different ways to do this. Ultimately, as long as you do it correctly, they'll result in the same answer. And one thing you could say is, well, r is right here. R squared is x squared plus y squared. So I could just square root this. And then the square root of r squared, which is r, equals the square root of that. So r is equal to the square root of x squared plus y squared. Equals 4 cosine theta. I got rid of the r right here, but I still have a theta floating around. And the question is, how do I get rid of that? You could try to do some weird tan inverse right here, which would give me theta, and then plug the tan inverse in there, and get this big, huge, messed up thing. We're not going to do that. There is actually another way to do this, and we'll just erase a step. The conversion I have to get rid of cosine is right here. X equals r cosine theta. I can convert to x, substitute into x, if I have an r cosine theta. I don't have r cosine theta, I just have cosine theta. So, multiply it by r. Just stick an r right there. Now I have r cosine theta. You guys know your algebra. I can only multiply an r on the right if I do the same thing on the left. So multiply an r over here. Then I get r times r squared equals 4 r cosine theta. Now substitute. Here, now instead of r, I have r squared is x squared plus y squared. So we can do that directly. Now I have 4 r cosine theta. That's 4. R cosine theta is x. That's 4x. Now I have an equation in terms of x and y. Again, that is completely fine. That's implicit. If you wanted to make it explicit, bring the x's and the y's and everything to one side. So you get x squared minus 4x plus y squared equals 0. And now something we'll see later on, this is the equation of a circle. So complete the square really quickly. X squared minus 4x, half of 4 is 2. Square that and you get 4, so add it. Plus y squared equals 0. You guys know the rule when you complete the square. If I add 4 on the left, I add 4 on the right. Now, this is a perfect square. It becomes x minus 2 squared plus y squared equals 4. And it's the equation of a circle. The center is at 2, 0, and the radius is 2. So again, some of these, once you convert, you can do the algebra and simplify pretty easy. Other ones are messier and it won't work. I was going to put either bearing or harmonic motion on this video, but it's already like 14 minutes long and YouTube will only let me upload 15-minute videos. So I'm going to stop this here and I'll have to make another video or two for the other material.